You know what the loudest event in the history of everything sounded like? Nothing. Absolute silence. Not because it was brief, not because it was weak, but because the very concept of sound had not yet been earned by the universe. And that distinction between no sound and cannot yet be sound is the most interesting thing anyone has ever failed to notice about the birth of everything. If you are new here, welcome to Silent Cosmos. Hit subscribe, find somewhere comfortable, and stay until the very end, because we are going to follow this silence all the way down through 13.8 billion years of cosmic history, and by the time we come out the other side, the word silence is going to mean something completely different to you than it does right now. Settle in. This one goes to the beginning of time. Part 1, the question that sounds simple, but is not. Let us begin with something everybody already knows. Sound needs a medium. Sound is not a thing that travels through empty space the way light does. Light is an electromagnetic wave. It is a self-sustaining oscillation of electric and magnetic fields that can propagate through a perfect vacuum without any medium at all. A photon leaving the surface of the sun can travel 150 million kilometers of essentially empty space and still arrive at your retina with full force. No medium required. Light does not need anything to lean on. Sound is completely different. Sound is a mechanical wave. It is a wave of compression and rarefaction, of tiny pressure fluctuations propagating through matter. The atoms in a medium, whether that medium is air, water, steel, or glass, get pushed together and then spring apart, and the disturbance travels through the material as neighboring atoms pass the push along to their neighbors. Sound is, in the most literal physical sense, atoms bumping into atoms and bumping into more atoms and bumping into more atoms, passing a mechanical disturbance along a chain of material contact, all the way from a vibrating source to a listening ear. Take away the matter and the sound stops. Full stop. You cannot have a sound wave with nothing to wave in. This is why space, as we experience it today, the vast dark vacuum between stars and galaxies, is almost completely silent. Not quite completely silent, because there are actual gas clouds between stars, and those gas clouds can carry very low frequency pressure waves. And there are places in the universe, enormous galaxy clusters, nebulae, star-forming regions where the gas is dense enough to sustain genuine acoustic oscillations that bear a structural resemblance to sound, even if the timescales involved stretch across millions of years. But when we talk about the open void between star systems, the interstellar medium in its most diffuse regions contains roughly 1 atom per cubic centimeter. Your breath, for comparison, contains about 27 quintillion atoms per cubic centimeter. The interstellar void is so sparse that for all practical purposes, sound cannot propagate through it. So the conventional answer to the question of why the Big Bang happened in silence is exactly this. The Big Bang happened in space. Space is a vacuum, and vacuums do not transmit sound. End of story. Clip. Subscribe. Except that answer is wrong. Not a little wrong. Not technically inaccurate, but mostly right-wrong. Wrong in a way that inverts the entire story. Wrong in a way that turns out to be far more interesting than the right answer has any business being. Wrong in a way that has taken physicists most of the past century to fully articulate, and that even today is still being refined with some of the most precise instruments ever built by human hands. The conventional answer is wrong because it assumes something about the early universe that is not true. It assumes the early universe was a vacuum, and the early universe was about as far from a vacuum as anything in the history of physics has ever been. To understand why, you have to understand what the Big Bang actually was. Because here is the second misconception, sitting right next to the first one, quietly corrupting your mental model of the event from day one. The Big Bang was not an explosion, it was not a detonation, it was not a bomb going off in an otherwise empty space, It was not a fireworks display. Every piece of popular imagery you have ever seen, the glowing point erupting outward into a black void, the matter flying in all directions from a central location, all of it is wrong in a very specific and important way. The universe did not begin with something exploding into a pre-existing emptiness. The universe began with the entire fabric of space itself beginning to expand. Everything, all of space, everywhere at once, simultaneously. There is no center, there is no location where it happened. It did not happen at a location. It happened at all locations at the same time, because location itself was part of what was being created and transformed. This distinction is not semantic, it is not a quibble about terminology. It changes every downstream conclusion about what the early universe was like, including, crucially, whether it contained the kind of medium through which pressure waves could propagate. And it did, in the most spectacular way imaginable. Part 2, the error in the picture you have been carrying. Before we can understand the sound, we have to thoroughly understand the wrongness of the explosion picture, because most people, even scientifically literate people who have read about cosmology, who know intellectually that the Big Bang was an expansion rather than an explosion, still privately visualize something like a firework when they think about the early universe. The image is so deeply embedded from textbooks and documentaries and popular science graphics that it takes a sustained effort to replace it with something more accurate. And unless you replace it, the silent story does not make sense. So let us do it properly. Let us take the explosion picture apart. In an explosion, there is a location where the detonation occurs. There is a center. The energy release happens at a specific point or region in a pre-existing space, and matter and energy fly outward from that center in all directions, expanding into the space that was already there before the explosion. The shrapnel from a bomb does not create new space as it travels. It moves through the space that was already there, space that was occupied by air before the bomb went off, and is now occupied by rapidly moving metal fragments. The Big Bang is not this, not even close. The Big Bang is the beginning of space itself. There was no pre-existing space for something to explode into. There was no ambient medium through which matter could travel. There was no outside region into which the universe was expanding. The universe did not expand into anything. The universe expanded as everything. The metric of space, the mathematical description of distance itself, began to change, and what we call expansion is the consequence of that change, not matter moving through a pre-existing arena. This is why the question of where the Big Bang happened has the strange answer that physicists give when students ask it, the answer that seems like a dodge but is actually the only honest response available. The Big Bang happened everywhere. Every location that exists today was part of it. The spot where you are sitting right now was at the Big Bang. The most distant galaxy that James Webb can observe was at the Big Bang. The location of Andromeda was at the Big Bang. The center of a black hole 40 billion light-years away was at the Big Bang. There was no location that was not at the Big Bang, because the Big Bang was not a thing that happened at a location. It was a thing that happened to location itself. This realization was formalized mathematically through general relativity, specifically through the Friedmann equations, which describe how the scale factor of the universe, essentially the number that converts coordinate distances in our mathematical models to actual physical distances, changes over time. In the Friedmann equations, there is no preferred point. The equations treat every point in the universe identically. There is no center. There is no edge. There is just a scale factor that is changing, and the consequence of that changing scale factor is that every pair of points in the universe has the distance between them changing over time. This is why the balloon analogy, despite its flaws, has been so persistently useful in cosmology. Not because the balloon surface is a perfect model of the universe, which it is not, but because it captures one essential feature that the explosion picture misses entirely. If you draw dots on the surface of an uninflated balloon and then inflate it, the dots all move apart from each other, and every dot sees every other dot moving away from it, and no dot can claim to be the center from which the others are fleeing, because there is no center on the surface of the balloon. Every dot is equivalent. Every dot experiences the same pattern of apparent recession. The expansion is intrinsic to the surface itself, not a motion of the dots through some pre-existing space. Now, the balloon analogy breaks down in important ways. The surface of the balloon is two-dimensional and curved into a three-dimensional embedding space, which our universe almost certainly does not require. Our universe appears to be spatially flat, meaning that the geometry of three-dimensional space obeys Euclidean rules at the largest scales, with no evidence of a curvature that would require an embedding into a higher dimensional space. And the center of the balloon, the point the surface is curving around, is not a meaningful physical location in our universe. But the intrinsic expansion, the expansion that is a property of the space itself, rather than a motion of contents through space, that is real. That is what the mathematics of general relativity describes. And once you have that picture firmly in place, the nature of the early universe becomes available in a way it simply was not before. Because if the universe is not matter flying through pre-existing empty space, if it is a spatial metric changing everywhere at once, then what was that spatial metric filled with in its earliest moments? What was actually occupying every point in space when the scale factor was tiny and temperatures were unimaginably high? And the answer to that question is what transforms the silence story completely. The early universe was not empty. It was the opposite of empty. It was the densest, hottest, most thoroughly filled volume of space that has ever existed in all of cosmic history. And that dense, hot material had a very specific property that matters enormously for our story. It could carry pressure waves. Part 3, the Planck epoch and the wall at the beginning. Go back as far as physics can currently take you. Go back to the very first moments of the universe's existence. Go back to a time so early that every number involved is a ratio of incomprehensibly small and incomprehensibly large quantities stacked on top of each other. We are talking about the Planck epoch, which lasted from time 0 to approximately 10 to the power of negative 43 seconds after the Big Bang. 10 to the negative 43. That is a decimal point followed by 42 zeros and then a 1. Written out as an interval of time, it is 0. Is 0 1 seconds. If you wanted to fit that many of these intervals into a single second, you would need to stack them 100 million, trillion of them deep. This is the Planck time, and it is the smallest meaningful unit of time that our current physics can describe. The reason it is the smallest meaningful unit is that it represents the scale at which the two great pillars of modern physics, general relativity and quantum mechanics, both break down simultaneously in the same place. Below the Planck time, inside the Planck epoch, we have no working theory. The mathematics of general relativity, which describes how space-time curves in response to matter and energy, returns infinities. And infinities in a physical theory are not answers, they are signals that the theory is being applied outside its domain of validity. And quantum mechanics, which tells us that at extremely small scales, reality becomes granular and probabilistic, conflicts with the smooth, continuous geometry of space-time that general relativity requires. We need a theory of quantum gravity to describe what was happening inside the Planck epoch, and we do not have one that is complete, confirmed, and universally accepted. String theory offers some possibilities. Loop quantum gravity offers others. There are several competing frameworks, each making different predictions, none of them yet confirmed by direct experimental evidence. So when you ask what was happening in the very first instant of the universe's existence, the honest answer from physics is that we genuinely do not know. what we can say is what emerged from this epoch. What we can trace backward to from observations of the universe today is a state that existed shortly after the Planck time, a state so hot and so dense that all four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were almost certainly unified into a single force. The temperature at this stage was so extreme that familiar particles like protons and electrons did not even exist yet. Quarks and leptons and the force-carrying particles lived in a kind of primordial unity, a symmetry that would not be broken until the universe cooled enough to allow them to condense into the structures we recognize today. This is a state of matter for which we have no laboratory analog. The most powerful particle accelerators ever built, the Large Hadron Collider at CERN, which accelerates protons to energies of about 14 trillion electron volts, cannot come close to recreating the conditions of this epoch. We are extrapolating backward from what we can observe into a realm that is genuinely beyond the reach of any instrument humanity has built or is likely to build. And here is the crucial point for our story. At these temperatures and densities, the concept of sound waves is not yet available in the way we need it. Not because the medium does not exist, the medium is very much present, but because the conditions are so extreme, because the energy scales are so far beyond anything familiar, that the physics of how pressure disturbances propagate through the medium is nothing like what we mean when we say sound. We are in the territory of quantum field theory, of quark-gluon plasma, of a regime so foreign that analogies drawn from everyday experience fail almost immediately. For sound in the meaningful sense, we need to wait, and we will not have to wait long as cosmic time is measured. But first, there is something else to deal with, something that happened immediately after the Planck epoch, and that had profound consequences for everything that would come afterward, including the conditions under which sound could eventually propagate. Part 4. Inflation and the speed no wave could match. The universe did not expand slowly after the Planck epoch. It did not emerge from its quantum gravitational infancy and then gently stretch into the cosmos we know today. Between approximately 10 to the negative 36th seconds and 10 to the negative 32nd seconds after the Big Bang, a window of time so brief that calling it a blink of an eye would be a profound understatement, the universe underwent a period of expansion so rapid that it is almost impossible to convey in words. This period is called inflation, and it was proposed by physicist Alan Guth in 1980 with significant subsequent development by Andre Linde and others as a solution to several problems that the standard Big Bang theory, without it, could not resolve. The flatness problem, which asks why the geometry of the universe is so precisely close to flat when small deviations early on should have been amplified dramatically over time. The horizon problem, which asks why regions of the universe that should never have been in causal contact with each other have the same temperature to 1 part in 100,000. And the magnetic monopole problem, which asks why the exotic heavy particles predicted by grand unified theories are not detected everywhere in the cosmos. Inflation solves all three of these problems in one stroke by proposing that a scalar field, called the inflaton field, existed in a metastable high-energy state in the very early universe, and that this field drove an exponential expansion of space so extreme that all the observable universe we see today, everything within our cosmological horizon, expanded from a region so small that it was well inside a single, causally connected domain, had time to thermalize, and then was blown up to cosmic scales in an interval shorter than anything imaginable. How rapid was this expansion? The most conservative models of inflation suggest that the scale factor of the universe increased by at least a factor of 10 to the 26th power during the inflationary epoch. More elaborate models suggest the factor may have been vastly larger. 10 to the 26th means that a region the size of an atomic nucleus became a region larger than the observable universe in a time interval that makes the Planck time look leisurely. This expansion was far, far faster than the speed of light. Not in the sense that anything moved through space faster than light, which would violate special relativity, but in the sense that the metric of space itself was expanding so rapidly that the distance between any 2 points was increasing at a rate that dwarfed the speed at which any signal, any photon, any pressure wave, any physical influence could travel. During inflation, the universe was not empty. Matter and energy were present in the form of the inflaton field itself and its excitations, but the expansion was so rapid that any pre-existing structure, any density fluctuations, any pressure waves that might have been building were smoothed out. Inflation is sometimes described as cosmic ironing, and the analogy is apt. The universe before inflation may have been wrinkled and lumpy in complex ways. Inflation stretched those wrinkles to scales so large that the portion of the universe we can observe today appears almost perfectly smooth. Almost but not quite, and the almost but not quite part is where the seeds of everything, including the seeds of sound, were buried. Quantum mechanics, which tells us that even the vacuum has intrinsic fluctuations at small scales, leaves a fingerprint on the inflaton field. Tiny quantum fluctuations in the inflaton field, at scales so small they were nearly infinitesimal, were stretched by inflation from quantum scales to cosmological scales. These stretched fluctuations became tiny density variations imprinted on the fabric of space, regions that were ever so slightly denser or ever so slightly sparser than the surrounding average, 1 part in 100,000. That is the amplitude of these primordial density fluctuations. They are the seeds that will eventually, hundreds of millions of years later, grow under gravity into the galaxies and galaxy clusters that fill the universe today, but they are also something else. They are the initial conditions for the universe's first sound waves, the first note of the cosmic composition, the very first musical setup in a universe that had, until this moment, been doing something so extreme that music was not yet a meaningful concept. Part 5. The medium appears. When inflation ends, when the inflaton field rolls down from its metastable high-energy state into its lower-energy ground state, the energy that had been locked up in the field is released as a burst of radiation and particles. This process is called reheating, and it is one of the stranger moments in cosmic history, a moment when a universe that had been dominated by a single, exotic field suddenly became populated with the more familiar denizens of the particle physics zoo. The temperature immediately after reheating was extraordinary. Estimates vary with different models of inflation, but typical scenarios place the reheating temperature somewhere around 10 to the 27th Kelvin. That is 10 million trillion degrees above absolute zero. For comparison, the core of the Sun is about 15 million Kelvin. The reheating temperature is about 100 trillion times higher than the core of the Sun, higher than anything that exists in the observable universe today, higher than anything that has existed since those first moments. At this temperature, everything we normally recognize as matter does not exist. There are no protons, no neutrons, no atoms. There are quarks and gluons, the fundamental constituents of nuclear matter, moving freely in a state called the quark-gluon plasma. There are leptons, the particle family, that includes electrons moving at nearly the speed of light in every direction. There are photons, there are neutrinos. There is a hot, dense, opaque soup of fundamental particles interacting with each other constantly, electromagnetically, through the strong nuclear force, through the weak nuclear force, in a furious, thermalized, equilibrated chaos. This is the medium. This is what fills the universe. This is what makes the silence story wrong. The early universe was not a vacuum into which nothing could propagate. The early universe was the densest medium that has ever existed. And a dense medium absolutely can, in principle, carry pressure waves. In fact, Pressure waves in a dense medium are something we understand quite well. We have equations for them. We have studied them in contexts ranging from the interior of the Sun to the laboratory study of quark-gluon plasma at particle accelerators. The physics, while extreme, is not beyond the reach of our theories. And the medium had another crucial property. It was not uniform. Thanks to those quantum fluctuations stretched by inflation, the early universe had density variations, not large ones, not visible ones. 1 part in 100,000 is a truly tiny variation, but it is not zero. And physics does not care whether the nudge is enormous or infinitesimally small. A nudge is a nudge. A density variation is a density variation. And in a medium that can carry pressure waves, a density variation will eventually drive a pressure wave. There is one critical additional ingredient needed to understand why pressure waves would actually propagate in this medium, rather than simply being statically frozen as density variations. That ingredient is radiation pressure. The early universe was not just filled with particles, it was thoroughly interpenetrated by photons, by electromagnetic radiation moving at the speed of light in all directions, and photons exert pressure. The pressure of radiation acts on the charged particles in the plasma, pushing them. When a region of the plasma is compressed by a density fluctuation, the radiation pressure in that region increases, pushing back against the compression and driving an outward wave. The region expands, overshoots, and the gravitational attraction of the matter pulls it back toward compression again. The result is an acoustic oscillation, a genuine pressure wave, the same physics at its most fundamental level that drives the sound in this room, in the air between you and whatever device you are using to watch this. Compression followed by rarefaction followed by compression, propagating outward through the medium. The Big Bang had sound, not quiet sound, not a gentle murmur. Sound waves that were the largest structures that had ever existed, propagating through a medium so hot and dense that the mathematics looks nothing like your everyday experience of acoustics, but obeying the same fundamental physical principle. Matter and energy in a medium pushing back and forth, creating oscillations that travel through the medium from one region to the next. The Big Bang was loud, the loudest event in the history of everything. Waves propagating through a plasma at approximately 60% of the speed of light. The scale of the disturbances was comparable to the size of the observable universe at the time. The energy involved was literally all the energy in existence, and nobody could hear it. But not for the reason you thought. Part 6. Why silence was still the answer. The sound was there, the waves were real, the plasma was oscillating, the energy was being carried through the medium in the form of acoustic disturbances on the largest possible scale. And yet if you had somehow been present in those first moments of the universe, you would not have heard anything, not because the waves were not there, they were, but because your ears are not the kind of detector that works for these waves, and the problem goes much deeper than the inadequacy of biological sensors. The problem is time, the problem is frequency, the problem is scale. Sound waves propagate at a speed determined by the properties of the medium through which they travel. In air at room temperature, the speed of sound is about 343 meters per second. In water, it is about 1,180 meters per second. In steel, it is about 500 meters per second. In the quark-gluon plasma of the very early universe, moving even faster. In the photon baryon plasma of the universe around 380,000 years after the Big Bang, the waves were moving at approximately 170,000 kilometers per second, over half the speed of light. But the scale of the waves was not meters or kilometers or light years. The scale of the primordial sound waves was on the order of the size of the observable universe at the time they formed. We are talking about wavelengths of tens of millions of light years, and the time it takes a wave to complete one oscillation is the wavelength divided by the wave speed. A wave with a wavelength of tens of millions of light years traveling at a significant fraction of the speed of light, completes one oscillation in an interval of time measured in tens of millions to hundreds of millions of years. Human hearing is sensitive to frequencies between roughly 20 Hz and 20,000 Hz, 20 cycles per second to 20,000 cycles per second. A tone at 20 Hz is so low that it sits at the edge of perception, felt more as a physical vibration than heard as a distinct pitch. A tone at 20,000 Hz is the upper limit of audibility, a thin, mosquito-like squeal that most adults cannot hear after their 20s. Everything audible to the human ear lies within this range. The primordial sound waves were completing one oscillation every tens of millions of years. One cycle every tens of millions of years corresponds to a frequency of approximately 10 to the negative 15th Hertz. That is a decimal point followed by 14 zeros and then a 1 cycles per second. It is 25 orders of magnitude below the lowest frequency a human ear can detect. 25 orders of magnitude. The gap between human hearing and the primordial sound waves is more than the gap between the diameter of a proton and the diameter of the solar system. There is no auditory experience that lets you understand how low this frequency is. There is no instrument a human could hold or carry that would produce this frequency. There is no analogy in human sensory experience for the gap between the frequency of primordial acoustic oscillations and the frequency range of human hearing. And yet a physicist at the University of Washington named John Cramer decided to try to let you hear them anyway. What he did is one of the most audacious and, frankly, delightful things in the history of popular science communication. He took the data from the cosmic microwave background, the Planck satellite's map of the temperature fluctuations in the oldest observable light in the universe, and he converted the temperature variations, which encode the remnant imprint of those primordial acoustic oscillations, into a sound file. He then boosted the frequency by approximately 10 to the 26th power, 100 septillion, a 1 with 26 zeros, to bring those oscillations from their actual frequency range into the range of human hearing. The result, updated using Planck satellite data in 2013, is a deep, rumbling, descending tone, not dramatic, not explosive in the way you might imagine. It sounds something like a very deep, slowly dying note, an enormous bass hum that drops in pitch and volume as it plays. The descent in pitch corresponds to the stretching of the universe, the expansion of space elongating the wavelengths of the oscillations over time, lowering their frequency. The fading in volume corresponds to the dilution of the plasma as the universe expanded and cooled. If you wanted to hear what the Big Bang actually sounded like, that recording is the closest anyone has ever come to answering your question. But it should be understood for exactly what it is. Not a recording of the actual event. The actual sound waves never reached your ears and never could have. It is a mathematical translation, converting patterns that exist in the cosmic microwave background data into an audio file using frequency shifts so extreme that calling it a recording of the Big Bang is a significant poetic license. It is a translation of patterns, but the patterns are real. And that reality, the reality of those patterns, is what drives the next chapter of this story, because those patterns, those frozen acoustic oscillations, are not just a curiosity. They are written into the structure of the universe in a way that continues to affect the distribution of matter right now, 13.8 billion years later. They are arguably the single most important set of data in all of cosmology. And reading them has told us things about the origin and composition of the universe that we could not have learned any other way. Part 7, the fog and the photograph. For the first 380,000 years of the universe's existence, there was no observable light. Not because nothing was emitting photons. Photons were being emitted constantly in enormous quantities from every charged particle in the plasma. But the plasma itself was so dense that a photon could not travel any significant distance before being absorbed or scattered by another charged particle. The universe was opaque. Light could not move freely through it. This state is something we can relate to in a way by thinking about fog. When you stand in a thick fog, light is being scattered in all directions by the tiny water droplets suspended in the air. You can see light, diffuse and sourceless light coming from everywhere around you, but you cannot see through the fog to any distant object. The light that was emitted by something 20 meters away is not reaching your eyes intact. It has been scattered and redirected and scattered again before finding you, losing all information about its origin in the process. The early universe was like a fog so thick that even photons moving at the speed of light were, for all practical purposes, trapped. They would move, get absorbed, be re-emitted, move again, get scattered, be re-emitted again, in a random walk through the plasma that made net progress essentially impossible. The mean free path of a photon, the average distance it could travel before interacting with a charged particle, was tiny compared to the scale of the universe. And during all of this time, those acoustic oscillations were doing their thing, the density fluctuations were compressing and rarefacting, the photon pressure was pushing back against the gravity that was trying to collapse the overdense regions. The plasma was oscillating on enormous scales, all of it hidden inside this opaque, glowing fog. Then, at approximately 380,000 years after the Big Bang, something changed. The universe had expanded and cooled to the point where the temperature dropped below about 3,000 Kelvin, roughly half the temperature of the surface of the Sun. At this temperature, something dramatic happened. The protons and electrons in the plasma, which had been moving too fast and chaotically to bind to each other despite their electromagnetic attraction, were now moving slowly enough for that attraction to win. They combined, protons and electrons joined to form neutral hydrogen atoms. The plasma, which had been kept ionized by the constant bath of high-energy photons, suddenly became transparent. This event is called recombination, which is slightly misleading because it suggests they were combined before and combining again. They were not. They were combining for the first time, but the name has stuck. And what happened to the photons at this moment is one of the most beautiful things in the history of the universe. When the plasma neutralized and became transparent, the photons that had been bouncing around in the fog were suddenly free. They could travel freely through space without being absorbed and scattered by the charged particles that had trapped them before. And they have been traveling freely ever since. Right now, as you read or listen to this, those photons are passing through you, through this room, through the planet beneath you. They have been traveling for 13.8 billion years. They come from every direction in the sky because the surface on which they were last scattered, which physicists call the surface of last scattering, was a sphere around us representing the moment of recombination. These photons are the cosmic microwave background radiation, the oldest light in the universe. The Planck satellite mapped them in exquisite detail. The temperature map, showing tiny temperature variations of about 1 part in 100,000 across the sky, is the oldest photograph ever taken. It is a photograph of the universe at 380,000 years old, just at the moment when the fog lifted. And here is the crucial connection to our story. Those temperature variations are not random noise, they are the imprint of the acoustic oscillations, the frozen record of the primordial sound waves, caught at the exact moment they stopped. When the plasma neutralized and the photons were freed, the acoustic waves froze in place. The density fluctuations that had been oscillating, compressing, and rarefacting in the plasma suddenly lost the photon pressure that had been driving them. The sound waves stopped, and the pattern of compressions and rarefactions at the moment they stopped, was imprinted on the distribution of matter and the temperature of the photons. It is as if someone took a photograph of the ocean at a specific moment and then the ocean froze solid. The photograph would show you the waves, locked in place, preserved. The cosmic microwave background is that photograph. It shows you where the plasma was compressed and where it was refracted at the moment of recombination. And because different modes of oscillation, different wavelengths of the acoustic waves, had been going for different amounts of time since the Big Bang, some had completed half an oscillation, some had completed a full oscillation, some had completed 1.5 oscillations, and so on. The modes that had completed exactly half an oscillation were at maximum compression, or maximum rarefaction, at the moment the sound froze. These modes left the strongest imprint on the temperature map. The modes that had completed a full oscillation were back to their equilibrium density, leaving essentially no imprint. The modes that had completed 3/2 of an oscillation were again at maximum, leaving a strong imprint. The result is a series of peaks and troughs in what physicists call the power spectrum of the CMB, the mathematical description of how much structure exists at different angular scales on the sky. These peaks are called acoustic peaks, or in a name that is perfectly designed to make cosmologists both proud and embarrassed, baryon acoustic oscillations. Baryon. Acoustic oscillations. The universe speaks, you just have to know what frequency to listen at. Part 8. Baryon acoustic oscillations and the universe's standard ruler. Baryon acoustic oscillations are among the most precisely measured phenomena in all of cosmology, and they are also one of the most useful. But understanding why requires following the story past the moment the fog lifted into the 13.8 billion years that followed. When recombination happened and the acoustic oscillations froze, the pattern of density variations was locked into the distribution of matter. The regions that were overdense at the moment of recombination remained overdense. Not because the matter stopped moving, matter has been gravitationally collapsing and forming structures ever since, building the galaxies and galaxy clusters we see today. But the statistical pattern of the density variations, the characteristic scale at which overdensities are most common, was preserved. That characteristic scale is determined by how far the acoustic waves had traveled from their starting points before the oscillations froze. A sound wave in the photon baryon plasma of the early universe, moving at approximately 170,000 kilometers per second for 380,000 years, traveled a specific co-moving distance before it stopped. This distance is called the sound horizon. Computed from the known physics of the early universe, the sound horizon at recombination corresponds to a distance in the present universe of approximately 490 million light-years. What this means is that in the distribution of matter in today's universe, galaxies are preferentially found at separations of 490 million light-years, not exclusively there. The acoustic peaks are not walls, they are a preference, a statistical tendency, a slightly elevated probability of finding a pair of galaxies separated by this distance. But the preference is real, measurable, and consistent with the prediction. When you survey the positions of millions of galaxies across billions of light-years of cosmic volume, when you compute the two-point correlation function, the statistical measure of how often pairs of galaxies appear at different separations, you see a subtle but unmistakable bump at 490 million light-years. A tiny, barely perceptible excess of galaxy pairs at this separation. A frozen ripple in the galaxy distribution, left over from a sound wave that propagated through the early universe 13.8 billion years ago and then stopped when the plasma went neutral and the photons were freed. The baryon acoustic oscillations scale, that 490 million light-year feature, acts as what cosmologists call a standard ruler. Just as a standard candle is an object of known luminosity that can be used to measure distances by comparing its apparent brightness to its known intrinsic brightness, a standard ruler is a feature of known physical size that can be used to measure distances by comparing its apparent angular size on the sky to its known physical size. And the baryon acoustic oscillations scale is the most physically well understood and precisely measured standard ruler in cosmology. Using it, cosmologists can measure the expansion history of the universe. By observing the angular scale of the BAO feature at different redshifts, corresponding to galaxies at different distances, corresponding to light from different epochs in cosmic history, they can map how the scale factor of the universe changed over time. They can measure the Hubble constant. They can measure the amount of dark energy. They can place constraints on the geometry of the universe and the properties of dark matter. This is not a quiet, marginal technique. BAO measurements are at the forefront of modern cosmological research. The Dark Energy Spectroscopic Instrument, DESI, which is a state-of-the-art spectrograph mounted on a telescope at Kitt Peak National Observatory in Arizona, completed its first year of observations in 2024 and released results that represent the most precise BAO measurements ever made. DESI mapped the positions of over 6 million galaxies and quasars across a redshift range from 0.1 to 4.2, covering an enormous swath of cosmic history, and extracted BAO signals with unprecedented statistical precision. The DESI 2024 results are currently among the most discussed findings in cosmology, in part because they hint at possible tensions with the simplest cosmological model. The data suggests that dark energy, the mysterious component responsible for the accelerating expansion of the universe, may not be perfectly constant over time, as the simplest cosmological constant model predicts. This would be a significant finding, one that may require modifications to our standard picture of cosmological evolution. It is not yet a definitive conclusion. The systematic uncertainties in the DESI data are being intensely scrutinized by the community, and further observations are needed to determine whether the hint of evolving dark energy is real or a statistical fluctuation. But the larger point is worth emphasizing. All of this precision cosmology, all of this ability to measure the universe's expansion history, all of this power to constrain the properties of dark energy and the geometry of space, traces back to acoustic waves that propagated through the plasma of the early universe for 380,000 years and then froze. It traces back to sound. The universe's sound, long since frozen and imperceptible, is still teaching us things that no other measurement can. Part 9, the moment of greatest expansion and the CMB's acoustic peaks. The cosmic microwave background's power spectrum, the statistical description of temperature fluctuations at different angular scales, is one of the most information-dense objects in the history of science. Every feature of that spectrum encodes something about the physics of the early universe. The position of the first acoustic peak tells you about the total energy density and geometry of the universe. The ratio of the first peak to the second tells you about the density of baryons, ordinary matter, relative to photons. The position of the third peak tells you about the density of dark matter. The overall amplitude tells you about the amplitude of primordial fluctuations from inflation. The Planck satellite, an ESA mission that observed the CMB with unprecedented precision between 2009 and 2013, measured this power spectrum to extraordinary accuracy. The data constrained the basic cosmological parameters, the Hubble constant, the density of ordinary matter, the density of dark matter, the density of dark energy, the spectral index of primordial fluctuations, the optical depth to reionization, with a precision that earlier generations of cosmologists could only dream of. But the acoustic peaks themselves are worth dwelling on. There are at minimum 5 clearly detected acoustic peaks in the Planck power spectrum, each one corresponding to a different overtone of the acoustic oscillations. The first peak, the tallest and most prominent, corresponds to the mode that had completed exactly half an oscillation by the time of recombination. The mode that compressed maximally, then froze. This peak is at an angular scale of about 1 degree on the sky. The second peak corresponds to the mode that had completed a full oscillation and then froze at 0 net displacement. This mode was at its equilibrium density at recombination meaning the photons in this mode were at approximately the average temperature, meaning this peak is lower. The third peak corresponds to the mode that had completed 1.5 oscillations, meaning it was again at maximum compression, and this peak is prominent again, though lower than the first, due to diffusion damping at smaller scales. This sequence of peaks and troughs is not just a beautiful pattern, it is a direct fingerprint of acoustic oscillations. It is the smoking gun. It is the evidence, frozen into the oldest photograph ever taken, that the early universe was resonating like an instrument. And the scale at which the peaks appear, the angular separation between them, tells us directly about the geometry of the universe, specifically that the universe is spatially flat to very high precision. The flatness conclusion follows from a simple geometric argument. The sound horizon at recombination has a known physical size in comoving coordinates. The angular size of a known physical object depends on the geometry of the space through which you are observing it. In a positively curved space, angles are larger. In a negatively curved space, angles are smaller. In a flat space, angles correspond to what Euclidean geometry would predict. By comparing the angular position of the first acoustic peak to the predicted physical size of the sound horizon, we can measure the geometry. The data says flat, with an uncertainty of about 0.5%. So the acoustic oscillations, the primordial sound of the Big Bang, have told us that the universe is flat. They have told us the density of baryons. They have told us the density of dark matter. They have told us the amplitude of inflation's imprint. They have told us things about the universe that would be deeply difficult or impossible to learn any other way. And they did this by oscillating in the plasma of the early universe for 380,000 years, leaving a snapshot in the cosmic microwave background and then stopping. Part 10. What stopped the music? The moment of recombination is, in a very real sense, the moment the music stopped. The plasma went neutral. The photon pressure that had been the driving force of the acoustic oscillations, the thing that pushed back against gravity and kept the waves oscillating rather than simply collapsing, disappeared. Without radiation pressure, gravity won. The overdense regions began to collapse under their own gravity, without any restoring force to push back against them. The acoustic oscillations froze, but froze is perhaps the wrong word, because it suggests that the oscillating medium was still there, just stationary. What actually happened is more like the instrument was destroyed at the very moment the music stopped. The plasma, which had been the medium, ceased to exist as a plasma. It transformed into neutral hydrogen gas, which has completely different physical properties. The acoustic speed in the new medium was radically different. The coupling between matter and radiation, which had been what sustained the oscillations, vanished. The world that could carry those particular waves ceased to exist. What replaced it was a new medium, a transparent medium, a universe of neutral hydrogen gas permeated by now freely traveling photons, cooling and expanding and darkening. For the next several 100 million years, the universe went through what cosmologists call the cosmic dark ages. Stars had not yet formed. Galaxies had not yet condensed. The universe was a sea of neutral hydrogen and helium, slowly gravitationally collapsing into the first structures, lit by no internal sources of light. This dark age was not silent in the acoustic sense. The collapsing hydrogen gas did carry pressure waves, but of a very different kind. The medium was now cold, diffuse, and transparent, with negligible photon pressure. Acoustic waves in this medium were nothing like the extraordinary oscillations of the plasma era. They were the quiet, slow stirring of gas under gravity, more analogous to the large-scale atmospheric flows in a gas giant's atmosphere than to the primordial sound of the Big Bang. The first stars formed somewhere around 100 million to 200 million years after the Big Bang. Massive, short-lived blue giants called population 3 stars. They burned bright and hot and died quickly in supernovae that began to reionize the surrounding neutral hydrogen gas. The universe gradually transitioned from a neutral, dark, quiet medium to the partially ionized, galaxy-filled, light-filled universe of today. And the sound, in any meaningful sense, was a quiet presence rather than a dominant feature. Dominant. Today, in the universe as it currently exists, there are real acoustic phenomena. The interiors of stars are driven by convective sound waves that carry energy from the nuclear burning core to the outer layers. Helioseismology, the study of oscillation, modes propagating through the sun's interior, has allowed us to infer the internal structure of our nearest star with astonishing precision. The same technique applied to other stars, called asteroseismology, is now a mature and productive field that has revealed the internal structures of thousands of stars across the galaxy. There are enormous sound waves in galaxy clusters, hot gas in galaxy clusters, heated by the mergers of cluster subcomponents and by the jets of active galactic nuclei, carries genuine acoustic disturbances. The Perseus galaxy cluster, 240 million light-years away, has been found to carry sound waves with a period of approximately 10 million years, far too low for human hearing, but unmistakable in the X-ray observations of the Chandra Space Observatory. But these are echoes, descendants, tiny downstream consequences of the primordial acoustic era. They are not the original music. The original music played for 380,000 years, reached its finale when the fog lifted, and then froze its final chord into the distribution of matter and the temperature of the cosmic microwave background. The universe has been carrying those frozen chords ever since, and the scientists have only recently learned how to read them. Part 11. A different kind of cosmic sound. There is another kind of wave that the Big Bang may have produced, a wave not of pressure, not of compressions and rarefactions in a medium, but of something more fundamental. Something that does not require a medium at all, something that travels not through matter but through space-time itself. Gravitational waves. When masses are accelerated, they disturb the fabric of space-time, and those disturbances propagate outward as ripples in the geometry of space and time at the speed of light. This is not a metaphor. Gravitational waves are as real as electromagnetic waves, and for most of the 20th century they were a theoretical prediction confirmed by indirect evidence but never directly detected. That changed on September 14, 2015. On that date, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected a gravitational wave signal that had been traveling for 1.3 billion years from the merger of two black holes, each roughly 30 times the mass of the Sun. The detection was made simultaneously at two LIGO sites, one in Hanford, Washington, and one in Livingston, Louisiana, separated by 3,000 kilometers, which ruled out local noise sources. The signal matched perfectly with the theoretical prediction for the waveform of two merging black holes. LIGO measures gravitational waves by detecting changes in the length of its 4-kilometer arms caused by the passing wave. The sensitivity required to make this detection is almost incomprehensible. The change in arm length that LIGO detected from the 2015 event was approximately 1,000th of the diameter of a proton. 1,000th of a proton diameter over a distance of 4 kilometers. It is one of the most extraordinary precision measurements in the history of physics. Since that first detection, LIGO and its partner detector Virgo in Italy have detected dozens of gravitational wave events, from merging black holes, from merging neutron stars, and from merging black hole and neutron star pairs. Each detection is a new window onto violent events in the universe that are otherwise invisible to electromagnetic observatories. But what does this have to do with the Big Bang? Everything. The inflation epoch is predicted by most models to have produced gravitational waves, not from any specific pair of colliding objects, but from the quantum fluctuations in the inflation field that drove inflation. Just as inflation stretched quantum fluctuations in the matter density field to cosmological scales, and created the seeds of structure. It should have stretched quantum fluctuations in the gravitational field to cosmological scales and created a background of gravitational waves that fills the entire universe. These are called primordial gravitational waves. They would form a stochastic background, a random noise of gravitational wave signals arriving from every direction in the sky, encoding information about the energy scale of inflation and the physics of the very early universe. If inflation happened, these waves should exist. If they can be detected, they would be the most direct probe we have ever had of the physics of inflation, of the event that set the initial conditions for everything that followed. This is not just a theoretical curiosity, it is one of the central observational targets of modern cosmology, and there are two primary ways to search for it. The first is the cosmic microwave background. Primordial gravitational waves would have left a specific imprint on the polarization of the CMB photons, creating a particular swirling pattern in the polarization map called B-mode polarization. The BICEP and Keck array experiments at the South Pole have been searching for this signal for years, and they have placed increasingly stringent upper limits on the amplitude of primordial gravitational waves. A definitive detection of primordial B-modes in the CMB polarization would be one of the most important discoveries in the history of science, a direct imprint of quantum gravitational effects from the first moments of the universe. The second approach is to directly detect the gravitational wave background with a space-based interferometer. And this is where the LISA mission enters the story. Part 12, LISA and the Silent Cosmos Beginning to Speak. On January 25, 2024, the European Space Agency's Science Programme Committee formally adopted the LISA mission, the Laser Interferometer Space Antenna, marking its transition from a design concept into an approved space mission with allocated budget, timeline, and industrial contractors. After decades of development, LISA is real, and it is coming. LISA will consist of 3 spacecraft, each roughly the size of a large car, arranged in an equilateral triangle in solar orbit, trailing the Earth by about 50 million kilometers. The sides of the triangle will be 2.5 million kilometers long, more than 6 times the distance from the Earth to the Moon. Inside each spacecraft, 2 test masses, gold-platinum cubes, slightly smaller than a Rubik's Cube, will float in freefall, shielded from all external forces. The spacecraft will exchange laser beams between themselves across the 2.5 million kilometer arms. By measuring changes in the length of these laser arms at the level of a few billionths of a millimeter, a precision that dwarfs even LIGO's extraordinary sensitivity, LISA will detect gravitational waves at frequencies between 1/10,000th of a hertz and 1/10th of a hertz. This frequency range is inaccessible to ground-based detectors like LIGO, which are limited by seismic noise at low frequencies. LISA will open a completely new window on the gravitational wave universe. It will observe the mergers of supermassive black holes across the entire observable universe. It will detect thousands of binary star systems in our own galaxy. It will map the gravitational wave sky in frequencies that correspond to some of the most interesting sources in astrophysics. And it will search for the primordial gravitational wave background from the early universe. The primordial background from inflation, if it is within the sensitivity range of LISA, would appear as a very faint, uniform noise that does not come from any specific direction, but fills the entire sky. Disentangling this from the foreground of astrophysical sources, the compact binary systems and massive black holes that will generate their own gravitational waves, is an extraordinary data analysis challenge. But LISA's design includes specific strategies to address this challenge, and the prospect of detecting an echo of the inflationary epoch in gravitational waves is one of the most exciting scientific possibilities of the next decade. LISA is currently scheduled for launch in 2035 on an Ariane 6 rocket from Europe's spaceport in French Guiana. It will operate for at least 4 years, with a possible extended mission of up to 6 years. It will be, by orders of magnitude, the most sensitive gravitational wave detector ever built. In June 2025, Thales Alenia Space signed contracts with OHB System AG for several key components of the mission. The development of the spacecraft and instruments is underway. LISA is not a dream. It is a machine being built right now. And when it launches and when it begins collecting data, it will be listening. Listening not with ears, not with pressure sensors, not with any mechanical apparatus that registers compressions and rarefactions in a medium, but listening in the most literal, physically meaningful sense available to us. Detecting changes in the geometry of space-time caused by sources so powerful and so ancient that the word ancient becomes almost inadequate. If LISA detects the primordial gravitational wave background, it will be, in a very real sense, hearing the Big Bang. Not the acoustic sound of the plasma era. Those waves were frozen into the CMB and the galaxy distribution billions of years ago, but the gravitational wave echo of inflation, the quantum fluctuations of space-time itself, from the very first moments of the universe's existence, still propagating through the cosmos in the form of ripples in the geometry of reality. This is what the title of this channel, Silent Cosmos, really points at. Not that the cosmos is silent, it is not. It is full of waves, oscillations, resonances at every scale. It is full of information encoded in the patterns of matter and radiation and space-time. But that information comes in a language that has no obvious translation into the human sensory experience of sound. And yet, with the right instruments, with enough patience, with enough ingenuity, we are learning to read that language. We are learning to hear what the cosmos has been saying since before there was anything to hear. Part 13, the problem with being there. Let us pause and be very honest about something that the science communication around the Big Bang often glosses over. Even if you had somehow been present in the early universe, even if the question of your survival in the plasma were not immediately fatal, you would not have heard the sound waves in any meaningful way. This is not just about the frequency being too low for human hearing. It is about something more fundamental. The physics of how you would interact with that medium is completely different from the physics of how a human ear interacts with air. Your ear works by having a thin membrane, the eardrum, that flexes in response to pressure variations in the surrounding air. The pressure variations move the eardrum, which transmits the motion mechanically to the cochlea, which converts the mechanical motion into electrical signals that your brain interprets as sound. The entire chain of transduction from air pressure wave to neural signal depends on specific properties of air, specific properties of the materials in your ear, and specific properties of the biological machinery in your cochlea that have been tuned by evolution over hundreds of millions of years to work in air at near ambient pressure and temperature. In the plasma of the early universe, you would not have an eardrum. You would not have any biological structure at all, because biological structures cannot exist at temperatures measured in millions or billions of degrees. The atoms that compose biological molecules, even the concept of an atom composed of a nucleus surrounded by electrons, does not exist until the universe cools to the temperature of recombination 380,000 years after the Big Bang. Before that, there are no atoms, there is no chemistry, there is no biology. This is not a technicality. It is a fundamental statement about what matter can and cannot do at different temperatures and energy scales. The universe, in its first 380,000 years, was a place in which the complexity required for any kind of sensing instrument, biological or technological, was physically impossible. Not practically impossible, not engineering impossible. Physically, fundamentally, thermodynamically impossible. So the silence, when we talk about the Big Bang having happened in silence, has a deeper meaning than we might initially reach for. It is not just that the waves were too low in frequency to hear, or that the medium was different from air. It is that there was, in those first 380,000 years, nowhere in the universe where an observer could exist. The universe was a place without observers, not for philosophical or accidental reasons, but for thermodynamic reasons. The universe was too hot for complexity, too hot for structure, too hot for anything that could receive, process, and interpret a signal. The Big Bang happened in silence because silence is not the absence of waves, silence is the absence of a listener. And for the first 380,000 years of the universe's existence, there were no listeners possible. This observation has a philosophical dimension that connects to one of the deepest questions in the foundations of physics and the philosophy of science. The question of what it means for a physical phenomenon to be real if there is no observer to observe it. If a sound wave propagates through a medium and there is no ear anywhere in the universe to detect it, in what sense did the sound exist? Most physicists would answer that the sound wave was perfectly real, regardless of whether anything observed it. The wave was a genuine physical disturbance in the medium. It had energy, it had momentum, it interacted with other structures in the medium. Its reality did not depend on observation. The universe was not waiting around to be perceived before having the right to exist. But the question of observation and what it means is one that resists clean resolution, even in the most fundamental frameworks of physics. We will return to it. Part 14, the first fires and the universe's second chance at sound. The cosmic dark ages ended, the first stars switched on. The universe, which had been cooling and darkening for hundreds of millions of years, was suddenly illuminated by sources of light for the first time since the era of the primordial plasma. These first stars, population 3 stars as they are called, were extraordinary objects formed from pristine hydrogen and helium with no heavier elements mixed in. They were almost certainly far more massive than typical stars today. Some models suggest they were hundreds or even thousands of times the mass of the Sun. These stars had short, violent lives. They burned their hydrogen fuel in millions of years rather than billions, and they died in spectacular supernovae that seeded the surrounding gas with the first heavy elements ever to exist in the universe. Carbon, oxygen, nitrogen, silicon, iron, the elements that would eventually build planets and life, were forged in the cores of these first stars and scattered into the interstellar medium by their explosions. The universe after the first stars was a richer and more complex place. It had heavy elements, it had the beginnings of galaxies, gravitational structures where gas was collecting and stars were forming at increasing rates. It had regions where density was high enough for interesting chemistry to occur, where molecules could form, where the beginnings of the complexity that would eventually produce biology were being assembled. And it had, for the first time since the plasma era, a medium with properties somewhat resembling what we mean when we talk about sound as an everyday phenomenon. The interstellar gas in these early galaxies could carry genuine acoustic disturbances. Sound waves in molecular clouds were compressing gas and triggering new bursts of star formation. Supernova explosions were driving shock waves through the surrounding medium. The universe was resonating with its second generation of acoustic phenomena. But these waves were all unimaginably different from the primordial plasma oscillations. Their scales were stellar, not cosmological. Their timescales were years or millennia, not millions of years. Their energies, while extraordinary by human standards, were utterly negligible compared to the energies of the primordial era. The universe had changed, the medium had changed, the physics had changed, and if any observer had been present, if some sufficiently robust and thermally stable sensory apparatus had somehow been floating in the interstellar medium of an early galaxy, would it have heard anything? In principle, yes. The gas in star-forming regions is dense enough to carry pressure waves. The timescales of the waves are too long for biological hearing, but the waves are real. The universe at this epoch was, for the first time, in a state where the concept of sound was no longer entirely inapplicable, but still unimaginably distant from anything like the acoustic environment that life on Earth would eventually experience. Billions of years of stellar and galactic evolution still had to occur before the conditions would exist for a planet with an atmosphere and liquid water and air at standard temperature and pressure and biological ears would exist somewhere in the cosmos, billions of years before the universe would produce something capable of asking why the Big Bang had happened in silence. Part 15. The Wheeler-DeWitt silence. There is a deeper level of silence in this story. A silence that is not about frequencies being too low for human hearing, or media being too exotic for biological sensors, or temperatures being too high for observers to exist. There is a silence that is ontological, that lives in the mathematics of physics at its most fundamental level, and that poses a question so uncomfortable that many physicists would rather not discuss it. In 1967, the physicists Bryce DeWitt and John Wheeler attempted to quantize general relativity, to write down a wave function for the universe as a whole, to apply the principles of quantum mechanics to the fabric of space-time itself. The equation they produced is called the Wheeler-DeWitt equation, and it is one of the most provocative pieces of mathematics in modern physics. Not provocative in the sense of being controversial or unaccepted. The equation itself is not disputed, but what it implies is profoundly, disturbingly strange. The Wheeler-DeWitt equation is the quantum version of the constraint equation that describes the universe as a whole in general relativity, and when you write it down, when you carefully apply quantum mechanical principles to the gravitational field of the entire universe, something is conspicuously, hauntingly absent from the equation. Time. There is no time variable in the Wheeler-DeWitt equation, not hidden, not implicit, simply absent. The equation describes the wave function of the universe as a function of spatial configurations of all possible three-dimensional geometries the universe might have. But there is no parameter t, no time coordinate, no variable that describes how things change from one moment to the next. The equation is timeless. The universe in this description is a single, static quantum object, a wave function that assigns amplitudes to all possible spatial configurations, with no intrinsic sense of one configuration coming before or after another. This is the problem of time in quantum gravity. It is the same problem we discussed in another context in a different video on this channel, but it has direct bearing on the question of why the Big Bang happened in silence, because it raises the possibility that the very framework in which we ask about the beginning of the universe is malformed. If the universe is fundamentally a timeless wave function, then there was no moment at which the Big Bang happened. There was no before, no during, no after. There was only the wave function assigning amplitudes to configurations, with some configurations looking like they correspond to the hot, dense plasma of the early universe, and others looking like they correspond to the cooler, more structured universe of today. The experience of time, the sense that the universe progressed from the Big Bang to now, may be something that emerges from the internal correlations within the wave function rather than being a feature of the wave function itself. This is not a fringe view. It is a mainstream position in quantum cosmology, developed by physicists including Don Page and William Wouters through a framework called relational time, and extended more recently by a growing community of researchers working on the foundations of quantum gravity. Carlo Rovelli has written extensively about this picture and its philosophical implications. The Wheeler-DeWitt equation remains the central mathematical result around which these discussions orbit. If time is emergent, if before and after are not fundamental features of the universe but descriptions of how certain parts of the universe's wave function correlate with other parts, then the question of why the Big Bang happened in silence is not just a question about physics. It is a question about whether the event we are calling the Big Bang had a temporal character at all in any fundamental sense. This is where physics transitions into the genuinely uncharted territory, where it shades into philosophy without anyone drawing a clear line of demarcation, and it is exactly where the story of the Big Bang silence points if you follow it far enough. Part 16, Inflation and Quantum Silence. During inflation, the universe was expanding faster than the speed of any signal, including light, could propagate. This means that the different regions of the inflating universe were causally disconnected from each other. A pressure disturbance in one region could not send any signal to another region that was being carried away by inflation faster than light could traverse the intervening distance. This causal disconnection has a specific implication for sound. Sound is a mechanical wave, and mechanical waves are the transfer of information, specifically information about local pressure and density, from one part of a medium to another. For a sound wave to propagate, the regions of the medium must be in causal contact. One region must be able to influence the next region on a timescale shorter than the oscillation period. During inflation, the expansion was so rapid that even the fastest possible signals traveling at the speed of light, could not keep up. The different regions of the universe were not in causal contact in the relevant sense. This means that even if the medium had the right properties to carry acoustic waves in principle, the actual propagation of any mechanical disturbance from one region to another was impossible during inflation. The wave could not outrun the expansion. This is a different kind of silence from any we have discussed, not the silence of the wrong medium, not the silence of the wrong frequency, not the silence of the absence of observers. The silence of inflation is the silence of causal disconnection, of regions of the universe that could not speak to each other because the universe was expanding faster than any speech could travel. But quantum mechanics, which governs the behavior of the inflaton field, was still producing fluctuations. The quantum vacuum was fluctuating. Pairs of virtual particles and antiparticles were flickering in and out of existence at every scale. And when these quantum fluctuations happened at scales small enough to be inside a causally connected region, they were real and they were being produced continuously. What inflation did was take these tiny quantum fluctuations, which were oscillating at sub-Planck scales in a causally connected region, and then expand that region so rapidly that the fluctuation was stretched to cosmological scales before it could complete a single oscillation. The fluctuation was frozen, stretched from quantum scales to scales large enough that they would never interact with each other during inflation. They would be imprinted on the metric of space as a classical density fluctuation. This is the process by which the seeds of cosmic structure were created. The quantum fluctuations of the inflaton field, frozen by inflation into classical density fluctuations, provided the initial conditions for the acoustic oscillations that would follow in the plasma era. The silence of inflation was the moment of seeding. The sounds of the plasma era were the germination. And the gravitational wave background, if it can be detected, would be the direct evidence of what was happening in the inflaton field during the silence of inflation. It would be quantum mechanics writing its signature in space-time geometry at cosmological scales. It would be the quantum silence of inflation speaking to us in the only language it can still use, gravitational waves propagating through the fabric of space-time. Part 17, Hearing the Data Speak. The question of the Big Bang's silence has a practical, empirical dimension that goes beyond the philosophical. We are not just trying to understand what happened, we are trying to measure it. And the measurement enterprise is ongoing, active, and producing new results regularly. The latest DESI results, published in 2024 and continuing to be analyzed in 2025, represent the state-of-the-art in BAO measurements. DESI is a spectrograph with 5,000 fiber optic positioners that can be repositioned in about 2 minutes, allowing it to observe a new set of 5,000 galaxies or quasars every few minutes. Over its planned survey, DESI will catalogue more than 40 million galaxies and quasars, creating a three-dimensional map of the universe that dwarfs any previous redshift survey. From this map, BAO signals are extracted using sophisticated statistical techniques, and the positions of the acoustic peaks in the galaxy power spectrum are compared to theoretical predictions. The comparison constrains the expansion history of the universe, the density of different components of the cosmic energy budget, and the properties of dark energy. The 2024 DESI results, covering the first year of data and mapping over 6 million objects in a redshift range from 0.1 to 4.2, found results broadly consistent with the standard cosmological model, but with hints of possible tension in the dark energy sector. The Hubble tension, the discrepancy between the value of the Hubble constant inferred from the CMB and the value measured from local distance indicators like supernovae and Cepheid variable stars, remains unresolved and is one of the most actively debated problems in cosmology. The DESI-BO data has provided independent constraints on the Hubble constant that add additional texture to this debate, though they have not definitively resolved it. Nancy Grace, Roman Space Telescope, NASA's next Great Survey Telescope, expected to begin science operations in the next few years, will extend BAO measurements to even higher redshifts and finer angular scales than any previous survey, probing the acoustic oscillations imprinted on galaxy clustering in an epoch that has been difficult to access until now. Roman will use BEO as one of its primary tools for measuring the properties of dark energy and the expansion history of the universe. The CMB itself is the subject of ongoing and planned measurement campaigns. The Simons Observatory in Chile, currently under construction, will measure CMB temperature and polarization fluctuations with sensitivity beyond what Planck achieved, searching for the primordial B-mode signal from inflationary gravitational waves and refining constraints on acoustic peak, positions and amplitudes. CMB-S4, a more ambitious ground-based experiment currently in the planning and funding stages, would push this program even further. And there is LISA launching in 2035, opening the gravitational wave window at millihertz frequencies, searching for the stochastic background from the early universe. We are not passively waiting for the universe to reveal its secrets. We are building instruments, conducting surveys, processing data, refining models, and every year getting closer to a complete picture of what happened in the first moments of existence. The primordial acoustic oscillations frozen into the CMB and the galaxy distribution are the primary data source from which that picture is being constructed. The silence has been speaking all along. We are just learning to read the lips. Part 18, what the silence really means. There is a human dimension to this story that I want to sit with before we approach the end, because the physics is extraordinary, the mathematics is beautiful, the measurements are astonishing, but there is something in the structure of the question, in the particular combination of loudest event and complete silence, that points at something about the nature of information and the nature of observation that has implications beyond physics. The Big Bang was the most energetically extreme event in the history of the universe. The energy involved was, literally, all the energy that has ever existed. The pressure waves it drove through the primordial plasma were the largest physical waves that have ever propagated through any medium in the history of everything, and yet for 380,000 years, those waves produced no information that could be retrieved by any possible observer anywhere in the universe, because there were no observers and there could be no observers. Information is a strange thing. In physics, we talk about information as something conserved, something that cannot be destroyed, something that is always in principle recoverable from the state of the universe, even when it appears to have been lost. The no-hiding theorem of quantum mechanics, proven by Samuel Brownstein and Arun Pati in 2007, establishes that quantum information cannot be hidden in a quantum system in the sense of being inaccessible to anyone who has access to the system. And the black hole information paradox, which asks whether information is destroyed when matter falls into a black hole and is later emitted as Hawking radiation, has been one of the most productive research questions in theoretical physics, precisely because the answer seems to be that information is always preserved. But information that is preserved in principle and information that is accessible in practice are very different things. The primordial acoustic oscillations of the early universe encoded enormous amounts of information about the initial conditions of the universe, about the density fluctuations planted by inflation, about the ratios of baryons to photons to dark matter. In principle, all of that information is still present in the universe today, encoded in the pattern of the CMB temperature fluctuations and the distribution of galaxies. In practice, it has been filtered through 13.8 billion years of cosmic evolution that has diluted, scrambled, and partially obscured it. The story of modern cosmology is largely the story of finding ways to read this partially scrambled information, of developing instruments precise enough to measure the tiny temperature variations in the CMB, of developing statistical techniques sensitive enough to detect the subtle excess of galaxy pairs at 490 million light-year separations, of developing gravitational wave detectors sensitive enough to measure changes in arm length smaller than a proton's diameter, of developing theoretical frameworks capable of translating the measurements into constraints on the physics of the very early universe. And the story is not finished. There are things we still cannot read. The physics of the Planck epoch, the very first moment, is still inaccessible. The precise mechanism of inflation, what field drove it, and what energy scale it operated at, is still unknown. The nature of dark matter, which makes up most of the matter in the universe and plays a crucial role in structure formation, is still one of the deepest mysteries in physics. The nature of dark energy, the dominant component of the universe's energy budget and the driver of its accelerating expansion, is still unresolved. The silence of the Big Bang is therefore not just a historical curiosity, not just a physics lesson about the nature of sound. It is a statement about the current situation of human knowledge. We are beings who came into existence billions of years after the events we are trying to understand, using instruments and techniques developed in the last century, trying to read information encoded at the earliest moment of the universe and preserved in imperfect and degraded form through an incomprehensibly long sequence of physical processes. We are like paleontologists who arrived on the scene billions of years after the organisms they study, trying to reconstruct life forms from their chemical fossils in rocks. But our fossils, the acoustic peaks in the CMB power spectrum, the BAO signal in the galaxy distribution, the potential gravitational wave background, are extraordinary in their richness and precision compared to anything biology could preserve. They encode quantitative information about physics at energy scales we cannot replicate in any laboratory, and we are learning to read them. Part 19, the question of the listener. Let us come back to the philosophical question that the silence raises because it has not been fully resolved by anything we have said. Even granting all the physics, even accepting that the early universe was filled with real acoustic oscillations in the plasma, even granting that those oscillations were in principle real waves carrying real energy and real information, the question of silence remains. Silence is not just the absence of waves. Silence is the experience of the absence of sound. It is a first-person phenomenon. It is what a listener hears, or rather fails to hear, in the absence of sound waves reaching their auditory system. And if there are no listeners, if there is nowhere in the universe, Part 21, the final realization. Come back to the beginning of this story. The question that opened it. Why did the Big Bang happen in complete silence? The answer is not a single answer. It is a layered architecture of answers, each one deeper than the last, each one revealing a different dimension of the question. And like all the best answers in physics, the final answer is something that would have been unrecognizable to anyone who asked the question before the relevant science existed. The first layer is the intuitive physics layer, and it is wrong. The Big Bang happened in space, and space is a vacuum, and vacuums cannot transmit sound. This is false. The Big Bang did not happen in space in the way an explosion happens in space. The Big Bang was the expansion of space itself, everywhere at once, and the early universe was not a vacuum, it was a hot, dense, opaque plasma that thoroughly, completely filled all of space, and that plasma could, and did, carry acoustic waves. The second layer is the frequency layer, and it is true but incomplete. The acoustic waves of the early universe were oscillating at frequencies so low, with periods of tens of millions of years, that they are 25 orders of magnitude below the range of human hearing. They could not be heard, not because they were not real waves, but because the human auditory system cannot respond at those frequencies. John Cramer at the University of Washington translated these waves into the human audible range by boosting their frequency by a factor of 10 to the 26th power, and the result is a deep, descending rumble that represents the closest anyone has come to hearing the Big Bang. The third layer is the medium layer, and it is the most physically interesting. The acoustic waves of the photon-baryon plasma era stopped when the plasma went neutral at recombination 380,000 years after the Big Bang. The medium that carried the waves ceased to exist. The waves froze. Their final configuration was imprinted on the distribution of matter and the temperature of the CMB photons, and this frozen pattern, called baryon acoustic oscillations, has been preserved for 13.8 billion years and is now one of the most precisely measured phenomena in cosmology. The fourth layer is the observer layer, and it is the most philosophically profound. For the first 380,000 years of the universe's existence, there were no observers, not because observers had not evolved yet, but because the physical conditions of the universe were incompatible with the existence of any structure complex enough to qualify as an observer. The plasma was too hot for atoms, and without atoms there is no chemistry, and without chemistry there is no biology, and without biology there is no sensory experience, and without sensory experience there is no listening, and without listening there is no silence in the experiential sense. The fifth layer is the gravitational layer, and it is the most forward-looking. Gravitational waves from the inflationary epoch, if they are within the sensitivity range of current or planned instruments, would be the most direct probe of the physics of the first moments of the universe. The LISA mission, adopted by ESA in 2024 and scheduled for launch in 2035, will open a new window on the gravitational wave universe at millihertz frequencies and search for this primordial background. If it is detected, it will be, in the most literal sense, a direct signal from the silence of inflation, a quantum fluctuation of space-time stretched to astronomical scales by the exponential expansion of the early universe. The sixth layer is the quantum layer, and it is the deepest. The Wheeler-DeWitt equation, the quantum mechanical description of the universe as a whole, contains no time variable. The universe, at the most fundamental level our physics can currently access, may not have a temporal structure in the way we experience it. The Big Bang may not have been an event in time so much as a configuration of the universal wave function, a region of configuration space that has high amplitude and that correlates with what we call the early universe. In this picture, the silence is not the silence of an event that happened in time, but that nobody was there to hear. The silence is the silence of a timeless structure, a wave function that does not have anyone embedded in it to experience sound. And perhaps this is the most honest and most complete answer. The Big Bang happened in silence, not because it was quiet, not because the medium was wrong, not because the frequencies were too low, not because observers had not evolved, but because the event itself, the genuine beginning of the universe, sits at the edge of what it is meaningful to say anything about in the language of physics as we currently have it. The Planck epoch, the first 10 to the negative 43 seconds, is where our theories break. It is where general relativity and quantum mechanics refuse to be reconciled. It is where the smooth geometry of space-time, the very stage on which acoustic waves perform, gives way to something we do not yet have the mathematics to describe. Before the Planck time, if before even makes sense in that context, was silence. Not the silence of absence, not the silence of a medium that cannot carry waves, but the silence of a regime of physics we cannot yet speak about. A silence that physics has drawn a wall around and labeled with an honest admission that is rarer in science than it should be. We do not know. We do not know what happened before the Planck time. We do not know whether time itself began at the Planck epoch, or whether the concept of a beginning is even applicable to the universe at that level of description. We do not know whether inflation happened exactly as our models describe, or whether some other mechanism explains the flatness, homogeneity, and structure of the observable universe. We do not know whether the gravitational wave background from inflation exists at a detectable level, or whether it is too faint for any instrument we could ever build. But we know an extraordinary amount of what came after. We know that the photon-baryon plasma of the first 380,000 years resonated with acoustic oscillations at cosmological scales. We know that those oscillations froze at recombination and left their imprint on the CMB and the galaxy distribution. We know that those frozen acoustic echoes are detectable with modern instruments and are telling us things about the physics of the early universe that we could not have learned any other way. We know that DESI and Roman and LISA and CMB-S4 and their successors will continue to refine this picture and push the frontier of understanding further back toward the beginning. The universe spoke loudly at frequencies far below human hearing for 380,000 years. Then it went quiet. And 13.8 billion years later, we built instruments capable of reading the frozen record of that speech. And we found, written in the statistical distribution of galaxies and in the temperature of microwave radiation filling the sky from every direction, the detailed acoustic fingerprint of the first 380,000 years of the universe's existence. The acoustic peaks, the baryon acoustic oscillation scale, the spectral tilt of primordial fluctuations, the sound horizon 490 million light-years in the present universe. The Big Bang happened in silence. The universe spent 380,000 years filling that silence with the most extraordinary acoustic performance in the history of physics. And then the medium went neutral, the photons flew free, and the music stopped. The concert ended 13.8 billion years ago. The recording is in the sky, available to anyone with the right instruments, encoded in the pattern of temperature fluctuations in the cosmic microwave background radiation that is passing through your body at this very moment. The oldest music ever made, frozen in the universe's most ancient light, still playing for anyone who knows how to listen. That is what the silence was. That is what it hid. And that is why the most important discovery in the history of cosmology is not the discovery of a sound, but the discovery of how to read the fossil of a sound that stopped before anything existed that could have listened to it. If you stayed until the end, thank you. This one took us somewhere that very few conversations about the Big Bang are willing to go, all the way down to the edge of what can currently be said about the origin of the universe, and to the honest acknowledgement that there is a wall at the very beginning that our physics cannot see past. That wall is not a failure. That wall is the most honest map of human knowledge ever drawn. The universe keeps the first secret. We are working on the rest. Subscribe to Silent Cosmos if you would like to keep listening. There is so much more the cosmos is saying at frequencies we have only just learned to detect, in languages we are still translating, in a silence that was never really silent at all. Sleep well knowing that right now, at this moment, the universe's oldest light is passing through you, carrying the frozen echo of a sound that started 13.8 billion years ago and stopped 380,000 years later when the fog lifted and the stars could finally be seen. The silence was never empty. It was full of everything that was coming next.